we're going to continue our delve into the non-ideal diode. And the way that we're going to do this, we're going to draw something very familiar. We're just going to do it DC. We're going to put our diode here, and oops, the resistor comes over. We will call this, well, I'm going to be consistent with the book. They have it the opposite way. Okay. And VD, this is all capital. This is VR, plus or minus there. And then they all share, I'm going to call it ID, but they all share the same current. And what we're going to do is we're going to use our diode model. We're just going to keep in the positive current range, positive voltage range. I'm going to call this VDD, indicating the double letter, indicating a supply voltage that's going to be constant. And what we're going to do from this point on is we're going to try to assess, well, what the voltage VD is. We want to know what this is going to be for a specific value of R. Okay? So this doesn't seem super difficult, because we can go ID is equal to IS E to the VD over VT, keeping those two things constant. And then we also know that ID is also equal to VDD minus VD over R. Those are our two equations. All I did here was equate these two IDs. And so what this looks like, logically like this, is that we have our curve that comes up here, which is this equation. And then looking at it from the same perspective, we end up with this line. So VDD, so it's going to cross when VD is equal to 0. We end up with VDD there. When VDD equals VD, okay, down here, the current should equal, or sorry, when VDD equals 0, the current should equal minus VD over R, and so that's going to be down here. It's a negative slope on this. In other words, as VD changes, as it goes from here to here, sorry, I did this wrong. This is VDD over R. My apologies. So that's our current I. Okay, we're just going to put I, and this is our voltage V, which means, so sorry, I had that backwards for a second there. As we have the voltage increase here, so this voltage, as it approaches where the current's going to be 0, where these are both equal to each other, we're going to have an intersection there. And really, the point that we care about is where these two equate, where ID equals ID. They have to, according to all the laws that we have about KCL and anything else. They have to, and that's at that intersection right there. So, mathematically, let's do it. IS E to the VD over VT is equal to, make sure I get it all on there. Okay, VDD minus VD over R. And this looks great because this is a constant, this is a constant, this is our independent variable that we're trying to find here. This is a constant, and you're going to go through and you're going to say, okay, well, let's take the log of both sides. Let's divide by IS. We take the log of both sides, so we get VD over VT is equal to natural log of VDD minus VD over IS times R. And then you say, okay, we got to get these two VDs together and solve for it. And you say, how are we going to do that? Well, I'm going to take the exponential of both sides. Okay, E to the VD over VT is equal to VDD. And we end up back where we were up here. There is no analytic solution. This may confuse you because you say, there is an intersection. Yes, there is. But we can't get there from here. We can't get that. We can't solve it directly for VD. And I think that most of you would have a conniption about this. or at least have a problem, and I understand that, but there's nothing we can do about it. Go. I encourage you to go and find a mathematical means to find this, but no analytic mathematical solution exists. So how would we solve that? Well, there's guess and check. You can go through and put in a whole bunch of VDs. There's also something called computerized guess and check, and so that's what we're going to do here. And so let's just pick out an R value. R is equal to 5K. Okay. We'll pick IS, what we did before. IS is equal to 1 e to the minus 15th. Okay. VT is equal to what I had before. We'll keep that there. And then I'm trying to think if there's anything else that we have in there. No, I kind of like that. And so what we're going to do is I'm going to make a range of VDs. And I know that my range is going to be between like 0 and 1. And so I'm just going to say VD is equal to 0. I'll make a whole, just to make everybody happy, I'll make a whole bunch of them. Okay? So we'll do this one, and I'll say ID, and I'll call it for the diode. And I'm going to do that top equation is equal to IS times the exponential of VD divided by VT. Okay? And we can plot that. We'll do that here in a second. And then we'll also say that ID, the resistor, according to the resistor, is going to be VDD, which we didn't specify. So, I don't know. Let's put in 5 volts on it. Let's put in 12 volts and be very original. 12 volts minus VD divided by our R value. Okay? And now we can go and plot. Let's plot our IDR on the whole horizontal versus our VD. And you shouldn't be surprised when I bring this up on the screen here. And you can't see it yet, so let's bring our display capture up. So there's what that looks like. Okay, and we just don't need that hanging out there, or that, or probably that. Okay, so that's not surprising. That's kind of the plot that I showed you was going to look like before. And then we're also going to plot IDD versus VD with a hold on. Okay, whoops. Okay, and you're going to tell me, well, that looks like crap. And that's true, and the new MATLAB stuff makes sense, but I just need to zoom in really well. Turns out that my range for VD is probably hideous. And I've got something wrong, so, which was, I've got the axes wrong. Let me hold off. I plotted these backwards. And so VD versus IDR. Some of you probably saw that. That's good for you. Hold on, plot VD versus IDD. Plot it this way, and we'll do an axis thing from 0 to, I don't know, what do we want to do? 0 to 1, 0 to 0.8, and then vertical we're going to go from 0 to, I don't know, 0.005. We'll see if that works. There, that works good enough for me. You can see the intersection that exists right there. Between those 2 points, and I can even grab a little cursor tool, and I think that's the right one. Now I've changed on me and I don't like it. There's my cursor tool, and you can see it's jumping across the actual discrete points in MATLAB, and I can zoom in and I can say, ooh, 0.7114 volts at 22.57 milliamps, and call that good. And then every time you have to find it, mathematically do this. So there are better ways here, right? And so here's what I'm going to do. The independents are the IDD and the IDR. And so IDIF is what I'm going to call this, is equal to IDD. So this is a little bit of MATLAB, a little bonus here, IDR. Okay? And I'm going to find the absolute minimum. Okay, IDX is equal to find the, well, okay,
we're going to do this. IDX is equal to the min of ADS of I diff. Because I diff, I'll show it to you here in a little bit. It says the index of that is that one, so IDD of IDX is, okay, IDR of IDX is equal to, and VD of IDX. And certainly that's pretty close to where I'm crossing those. But let me show you exactly what I was doing there. If we plot the IDIF, it's going to be just a weird curve like this, and it's always going, and it's going to cross, and the minimum of it is negative 0.024. I don't want the minimum. If we want to find the intersection of two lines, I want to find the absolute minimum. And just to illustrate this just a little bit, just so that we can understand what's happening here, or what we're looking for. Sorry, my desk is a mess as normal. I'm just like you. Or maybe you're better than me. Okay. The whole point is, if I took two lines and I subtracted the difference to find this point, if I wanted to find it, this would be called a computer solution. Okay, you know, it's basically guess and check computer-wise. And if I want to find that closest point to each of those, I would subtract each one of those. But that's just going to give me, if you pay attention, that's just going to give me a line. So our minimum is going to be way down here. What I really want is where that crosses 0. Okay? And so there's a certain point. So if you take the absolute value, this guy starts coming up. And it's hard to see with my little graph that I had, but that point will come up. And so I want the absolute minimum. I want the absolute minimum difference. Because as one of these becomes bigger, so the difference here is positive, the difference here is negative. As this grows bigger this way, we get a more and more negative number. The minimum isn't going to do us any good. The other thing that I did with this is I used the min command, and just so that we're all on the same page, if we type a help min, it's going to give us all sorts of stuff, but probably the most important part about looking at this is that it will return two values. Also returns the indices into the operator, okay? And so this returns a minimum index value. That index value was what I found before, which was the 7112. So let's go back and plot. And then do my axis that I had. So axis just zooms me into a certain point right there. And what I'm going to do is I'm going to plot the same guys, but I'm going to do it with the index that we had there, and I'm also going to do an X. And you can't quite see it because it's teeny tiny, and you aren't seeing this because, okay, there's a teeny tiny X right there. Let me fix that. Marker size, I'm pretty sure that's what it is. Once again, help plot will help you with this. And I'm going to do 15. There's our marker. Okay. I'm also going to do the same thing, but in this case, I'm going to do IDR. And they're going to look like they're right on top of each other because I did such fine resolution. When I made my VD, if you remember, when I made my VD, I did in 100 microvolt steps. And so we can get within 100th of a microvolt, within a tenth of a millivolt using this system. And so depending on what you want. So every time we have, forget the ideal, non-ideal diode, right? For every program, we have to run this program, write a program, put it in, figure out what the voltage is, and that's how we're going to solve it, right? Well, you can do that, and people who have done that have written software like multisync, where multisync will go and calculate all this stuff. It'll do some kind of iterative program to figure out the diodes, and you can do a simple calculation or a rough calculation. You can put in ideal diodes if you want, or you can put in non-ideal diodes. But the fact of the matter is, you don't want to do this if you're doing homework on it, or if you're trying to understand what's going on, especially if what we're trying to do is change this into something that makes sense. And let's go back to how we started this lecture series. The lecture series started with something about if we were to actually plot our diode voltage on a half-wave rectifier, that we wouldn't get this perfect. And let me blow it up even bigger. We're going to go through and I'm going to exaggerate this a little bit. We're going to get this clipping. And we don't want to do every single point go through the equation. We can do it with a computer, but we're engineers. We want to be smart about this, and so we don't want to have to do the hard work. And one of the things that I always say is that we as engineers are lazy. We are lazy to the point where we will do that. We have an equation that will do something for us. So it's a weird kind of lazy, but we want to do something. We want to do something more efficiently. Is kind of what it is. That's the definition of being lazy right there. So doing it with the exponential model, we could do it with computers. We could put everything in simulations. We could have that do it for us. We still have to understand the basics, but probably the better method is just to do an estimation. And if you look at the plot that we have here, and let me put the plot back up here. We're going to go to our standard, and some of you in class have already mentioned this, but you come here and you say, for most of this, for the vast majority of this, up until we get to really teeny tiny, look how small that current is. That current is in the microamp range. Up until we get down to the microamp range, okay, hundreds of microamps. Up until we get to there, and even below that, it looks a lot like 0.7 volts. So a 0.7 volt model, I'm going to switch markers here. 0.7 volt model, we have a diode. That's better. And I'm going to denote that it's non-ideal. Okay? What we can do is replace it with 0.7 volt. A 0.7 volt source with that. So we just replace it point for point with one of these. And if we don't have 0.7 volts across this, it turns back into an open circuit. That's a really typical thing. So in order to, that's the problem with this marker, but in order to kind of do this, so I'm going to put in VS. There's our diode. We're going to replace this, remember, in our minds with this, and I'm actually going to, watch this. We're going to put in the voltage source here, 0.7, and that's so we can just add these directly together. So remember, this is kind of replacing that one. We have our R load, and we're measuring this voltage of our R. And we're just going to put in variable values for VS. I don't like that marker either, so we're going to switch back to blue. And so as we put in VS, as we have our VR on this, let's just put in some 0.5, 1, 1.2, 1.8. You can see those are the ones that I was thinking of from before, and we can throw in some values that we'd like to throw in there. So if we put in -1, we obviously know that we're reverse biased. This is one of the obvious cases. We're going to get 0, 0, we're still reverse biased. 0.5 volts isn't enough. If we add up this 0.5 and 0.7, we're going to get -0.2. We are not positive yet, so that diode is still reverse biased. So that's going to be 0. Now, just so we're clear, this is not generating 0.7 volts. If we don't apply anything, nothing will be there. But what it is doing, it's opposing 0.7 volts. Okay? And this one, finally, we get 0.3 volts, 0.5 volts, 1.1. We can just treat it just like this. And the reason why this is nice is when we plot
and we rectify, I'm going to blow this up here a little bit, we can just do a difference of 0.7. Now it's not perfect. These little corners here are going to be, but look, it's just a little corner here that we have to worry about. And we aren't even worried about that for this entire thing. But we end up with something that looks, that we can understand. And the cool part is we're going to be able to see this in lab. We're going to put this in here. This does put some limitations on our rectifiers, and that's kind of what I wanted to point out about all those rectifiers. Think about when we go back. When we go back, think about how many diodes you have to go through for each of those rectifiers. And that's how much voltage drop you're going to get. And so that's lost power, that's inefficiency. Let's just do a little bit of thought on this as well. You can stack these diodes, and so we've got this 10 volts. This is an example out of the book. I'm going to stack 3 diodes, and then that's a ground. And the cool part is we can just say, look, it looks like there's current going through them. We just have to make sure. And each of these is 0.7, which means this combined is going to be 2.1 volts. Sure enough, it still looks like they're forward biased. Current is going through them. And we're going to put a 10 kilo ohm resistor on this. Okay? And the only other thing that we might want to find out is what the current going through there, is going to be. So we have that current, in this case, is equal to the 10 minus the 2.1 divided by the 10K. And this is going to equal something like, let's see, that's going to be 7.9, so 0.79 milliamps, making sure that you can see that. And so that's really cool, but going back just really quickly, so this is why it matters. Half-wave rectifier, we get half-wave rectifier, okay? We're going to draw this kind of big. We're just going to do one waveform, like this. Half-wave rectifier, you're going to end up with something like this that has a 0.7 volt drop. Obviously, if you get into like 20 volts, 0.7 volts is less than 10% of that. You know, it's less than 5% of that. And so that's going to cause a little heartburn. When you go to the bridge rectifier, each time you pass current, it's going to go through two diodes, and so you're actually going to have a 1.4 volt drop, and so you're less efficient. The bridge rectifier is good. The bridge rectifier, so that was the bridge rectifier. The full wave rectifier is going to give us that 0.7 volts drop, but there's a downside to that, which is one's the transformer, and one is that we're going to have more reverse bias voltage on those diodes. Can they handle it? That's one of the questions we have to ask in the future. Can they handle it? And so that's a really good, I think that's a good place to stop. And we'll do one more. This is actually an important intro for the rest of it in small signal, large signal type of configuration. Actually, we're going to hold this off to the next lecture. I'll do a quick lecture about the small signal, large signal, and maybe we'll talk about xenodiodes